So in the last class, we began with chapter number 8, so confidence intervals, and we looked at one example of the first situation where sigma, when it is known, how to calculate confidence intervals. Let's look at case number 2, or second situation. Confidence interval for population mean when sigma is unknown. So that was the second example or formula that I provided. X bar plus minus, when sigma is not known, we use a distribution called T, and we calculate T alpha by 2 and then S divided by square root of n. In this formula, this part, if you recall, is your standard error. So we called it standard error, not standard deviation, just to differentiate that this is the variability in the distribution of means. So X bars or central, because of central limit theorem, if you take repeated samples, calculate X bars or means, and create a distribution, so it will have a variability of S divided by square root of n. So as sample size goes up, variability goes down, so all those things. This part, the entire thing after plus minus, so this part we call margin of error. After the plus minus term, whatever we have, we call that as margin of error. And another thing that you see here in this formula is this part that we called point estimate. So any confidence interval is made up of like different parts. One is point estimate, and then you have margin of error, and within that you have standard error. And then in the first example we had Z when sigma was known. In this example we have T when sigma is not known. So that's the only difference. So T is another distribution actually developed by one of the statisticians who used to work in, I think, England, in a factory where they were like making beers, and they used to collect data, do some analysis. So he figured out that especially when you are dealing with small samples, it is better to use T distribution compared to normal distribution, because there are some benefits of using T distribution, and the benefit is that it is more accurate. You get more accurate estimates for the population mean if you are using T distribution. So your normal distribution, as you know, looks like this. I'm trying to make another one. This is normal distribution, but for Z, standard normal distribution with mean 0 and standard deviations is 1. So for Z, mean is 0, standard deviation is 1. And the other distribution that I made is T distribution, which also has a mean of 0. Normal distribution, and this is T distribution. This T in the formula, that's what I'm referring to. So this T distribution is that T in the formula. So if you want to calculate, let's say, how much is the area to the left of -1? In this side you have +1. So if you are interested in probability that Z is less than -1, so for that we have already used this many times. To get probability we do P NORM, and if you say -1, it will calculate the probability to the left of -1. If you don't provide anything else, it will assume that you're talking about Z distribution or standard normal variable where mean is 0 and sigma 1. You can even write like -1 and then comma, provide mean 0, comma, provide standard deviation 1. But if you don't provide, then it will assume that we are using standard normal distribution. So if you use this, so let me go to Posit Cloud, type p norm, and select, put -1, run, we get 0.158. So I will use that as an area to the left of -1. And then if you want to do same thing for t distribution, so we start with p, and then for t distribution simply say t. And then again you can say -1. But it also needs degrees of freedom, df, which in this case is sample size -1. So for normal distribution, it never asks you like what is your degrees of freedom or what was the sample size. But here it is going to ask your degrees of freedom. So let's say we have like means based on samples of size 3. So sample size is 3, then degree of freedom will be 3 minus 1, 2. So that one gives you 0.211. So let me write down. So this area to the left of -1 for normal distribution we got was 0.16 if I round this to second decimal. 16% probability that the area is less than -1. So this area is 16%. Same thing here. T less than -1. To get this, what I did was I used P, T, and then -1, and I assumed a sample size of 3. So if you are using 3, then 3 minus 1 is 2. So this probability we got 0.21. So this is based on sample size 3. If you look at the shape of the distribution, they look similar. Mean is same, mean is at 0. Both are symmetric distributions. Area to the left of 0 and area to the right of 0 is 50-50. So it's a symmetric distribution, just like normal. But when you calculate area, they don't look same. You get 16% here, but you get more area to the left of -1 for t distribution. You can say like the tails here. So area in the tails, you have more value for t distribution. So tails are basically thicker compared to normal distribution. So that's one key difference between the two. Now if I repeat this, if I calculate the probability using t distribution that the value is less than -1, but if my sample size goes up to 30, so if sample size is 30, degrees of freedom is always -1. So 30 minus 1 is 29. So I have to use 29 here. If you put that, you should get 0.163. So central limit theorem, we talked about like every distribution becomes normal distribution when n is more than 30. So you can see that the value in the tails also start coming closer. So it is still slightly higher, but it is much closer compared to the first situation. And if I have like a sample size of 100, so sample size of 100 means we are taking samples of 100, calculating x bar, another sample of 100, calculating x bar, another sample of 100, calculating x bar. So if you are doing that, then what is the area? So 99 is almost like same as what you have for normal distribution. So basically when sample size goes up, it doesn't matter whether you use t distribution or z distribution, normal distribution. But when sample size is small, it matters a lot. Like if you are estimating like demand for, let's say, cars next year, so calculation of 16% versus 21% could mean like millions of dollars. So that's a big difference. So if you are given a situation where sigma is not known, t distribution we can use very easily. But you can use normal distribution if your sample size is really very high. Anyway, we are using computers for doing these calculations. It's not that you are gaining something in computing time. You're not going to save a lot of time just because you are using a normal distribution. This number here is n minus 1. Sample size minus 1. And it is also called degrees of freedom. Degrees of freedom is a statistical concept. You have already seen this earlier. If you recall formula for standard deviation S, so that was total of x minus x bar whole square divided by n minus 1. So this n minus 1 in the denominator is degrees of freedom. So degrees of freedom in a simple language means how many independent terms you have in any given equation. How much freedom you have. If I give you one small example, if you have, let's say, A plus B plus C is equal to 10. Suppose that is the equation. And with full freedom, you can choose any value of B, A, B, or C. So with full freedom, you choose, let's say, A to be 2. And you choose B to be 5. Now, do you have any freedom left to choose C at will? You don't have that freedom now. So as soon as these two are fixed at 2 and 5 and the total is 10, then the third value has to be 3. So there is no other option. You don't have any freedom left to choose C. So although you have like 3 unknowns, you have only 2 degrees of freedom. So basically, how many independent choices you have or how many independent terms you have in any given equation is degrees of freedom. It's like if I have a stick and if I have to cut that stick in 3 pieces, how many cuts do I need? To cut a stick in 3 pieces, how many cuts will be required? 2. So you need 3 pieces, but 2 cuts will do it. So you have 2 degrees of freedom. Key idea here is that when number of constraints or difficulties increase, freedom comes down. Especially like when you are using any distribution, you may have to figure out few things. And like to calculate this confidence interval, you have to calculate x bar first or standard deviation first. So that brings down your freedom one by one. But in this case, degrees of freedom is n minus 1, very simple. When we go to situations where we are comparing like 2 different products, 2 different designs of products, their degrees of freedom could be more complicated. Let's look at one application of this second case, case number 2. You do a study of hypnotherapy to determine how effective it is in increasing number of hours of sleep. You measure hours of sleep for 12 subjects, and the data is given below. 8.2 hours, 9.1 hours, and so on. Construct 95% confidence interval for mean. Number of hours slept for the population from which you took data. So we are assuming normal distribution, and it doesn't say anywhere what is population sigma, so which means that this is a second case, case number 2, sigma unknown. So this is going to be try it, 8.5. So the first thing we'll do is, because we have these values given, 8.2, 9.1, and so on, so we need to feed that data. So I will store that in X by pointing arrow towards X. And then to enter the values, if you recall, we use C and then parenthesis. And within parentheses, we enter all the values. Let me copy and paste these numbers. Now, we know that this semicolon will not work, so I'll have to change that to comma. Once you run that line, you can see in the third window, X values 1 to 12, and all those values are accepted. And now we need this format. So we'll do the same thing that we did last time. Let's call this solution 2 to differentiate from the previous one. So this is name given by us, and then within that we can store tsum. So as you start typing, you see tsum.test, select that. So instead of Z, we are using T. That's the only difference. Other things are similar. So we need mean, MEAN dot X, mean of random variable X. Now we are not given mean. Like there we simply put the mean because in the problem average was given as 36. Here we are given the data. So data is in X. So to find mean, we can say mean X. So that will calculate mean and provide the mean value. And then I'm putting a comma after this, and I will hit enter to keep it clean. And then we use sigma is not there because this is sigma unknown. So S dot X. So this one, where we need to give standard deviation. So we can get standard deviation using SD. So SD, and then in parentheses, if we say X, it will use all these X values and calculate standard deviation and use that number. Third number that we had input was sample size, n dot X. So n dot X. How much is n dot X? How much is the sample size in this case? 12. So you have 12 data points. So that is going to be 12. What else? Confidence level. So earlier we had confidence level, so we need confidence level for confidence intervals. So choose conf dot level equal, we say 0.95. So do not write 95 there, but confidence interval will be in terms of between 0 and 1. And that's it. So if you run this, what it will do is, it will run this and store everything in solution 2. You may see at the bottom there is some warning message. So in R, warning messages are okay. It's not an error. If it gives you warning, it's okay. We say solution because that's where our analysis is. So we choose solution 2 and put a dollar sign. To extract what we need confidence interval, so conf.int. So when you run that, you get 8.16, 9.80. We were given that sample size is 12, confidence level is 0.95, and then we were given some x values from which we calculated. So 95% confidence interval for population mean tsum.test, and we provided mean.x as mean of x, put a comma, s.x as d of x, we put a comma, sample size 12, and confidence level 0.95. So this is what we used in R. And we got the confidence interval as 8.16 to 9.80 hours. So people sleep about 8.16 to 9.8 hours. So what does a 95% confidence interval mean? So it's not that 95% of the population sleeps between 8.16 and 9.8. We are not talking about that when we talk about confidence intervals. So 95% confidence interval here means if we take 100 different samples and create 100 different CIs or confidence intervals, 95 out of 100 will contain. So if this process is repeated 100 times, 95% of the time we may be able to catch the actual value within the range of confidence intervals. So it means that. It doesn't mean that 95% in the population sleep between 8.16 and 9.8. Anybody has any questions? So there is a saying in English, I hear, I forget, I see, I remember, I do, I understand. So things that we hear many times, like most of the lectures that you hear in classes at UMass Dartmouth, everything is going to evaporate very soon. Sometimes like even while you're sitting in the class or as you walk outside the class, everything is going to go away. Things that you see, some examples or application, you may remember for slightly more time, but things that you do with your hands, your own hands, so those are the things that you remember for. In fact, you understand, so that's why you could remember for more time. So let's do a team activity, and where you are going to apply this confidence interval idea. Case number 2. So you will generate like some samples in the class and use that sample, feed in R or Posit cloud, and use the functions that I showed you, find the confidence interval, compare two different situations, and that's it. So this will be done in a group or team of 3 people. Instructions: collect data on flight time. So each team is a company which makes helicopters, and there are 2 designs, design 1, design 2. So you will be making that helicopter although it is a paper helicopter, because in the class we cannot do real ones. So you fly these helicopters, get the timings, 10 each. So you need a paper for paper helicopter, and you need a rectangular design. So when I say design 1 is 8 centimeter in length, I mean the length of this paper is 8 centimeter. So this rectangular paper is 8 centimeters long and width 2.5. So by that I mean this width. So this width is 2.5 for the first design and slightly smaller for design 2. How this is manufactured? You cut from the top up to about like 50% of this rectangle, and then maybe 25% cut on sides so that you can fold at the bottom like this. So it will look like this after folding at the bottom, and you have like only this helicopter has only 2 wings. So if you separate these two, you will see 2 wings. If you don't separate them, if you keep like this, it may not fly. But we don't separate like 90%. This angle should not be 90%, maybe 45% or 45. And then from certain height, you drop it and the wings will rotate and it falls to the ground. The time it leaves your hand and the time it touches the ground, so that is called flight time. So obviously you need, in the team, you need a pilot. So you may have to designate a person who will do that flying. So there is a pilot. There has to be somebody who is going to record time. And then maybe third person who writes down. So you need at least 3 people. So make sure you divide the work among 3 of you. So take 1 form, each team, and take 1 paper for your experimental designs. So I have rulers, I have scissors, so you can use all that. Two, three.
Oh.